put on this. Yeah. So now we start the course of Fourier analysis, but in very abstract way. So we write the first part. Elements of functional analysis. Now we do not follow any book because, of course, I will give you some book where you can read all this, but it would be too much. It would be very long. First, what we need the notion, abstract notion of distance, because we would need the notion of convergence of series, but not of numbers, but of functions or something else. So first part, metric spaces. Metric space. For functional analysis, if of these parts, maybe 5-6 lectures, but we shall do this, I hope, quickly. For example, if you have a real line, on real line, you have the notion of distance between 2 points, x and y. You know this distance rho. It is just the difference between these 2 points in absolute value. So we can measure distance between any 2 points. We can measure distance between any 2 points. What are the properties of this function? Its properties. First, this function is non-negative. Second, this function is equal 0 if and only if it is just the same point. If points are different, distance is non-zero. Third, it is symmetric. The distance from point x to point y is the same as distance from point y to point x. And fourth, triangle inequality. So when you was in school, you knew such thing. So if you have triangle, so for example, x, y, z, then you knew that the third side in usual geometry is less or equal than the sum of 2 sides. The same can be proved for this one-dimensional case, such absolute value. So we can prove x, y is less. It is done just by opening absolute value. So consider different cases. X, z plus rho, y, z. Triangle inequality. Or inequality. So these are the properties of distance on real line. Now it's good moment to illustrate you the general development of mathematics. How mathematicians, if you would, I'm not sure that somebody would become mathematician, but how they do progress, how they move from one model to another. They have very simple real line. They have very simple distance. They considered all its properties. These are more or less theorems. They are mini theorems or propositions. You should prove this by using properties of absolute value. Now they tell, consider any set and any function of 2 variables which satisfy these properties as axioms. So, example, what is the evolution of mathematics? Evolution of mathematics. First example, simple example. What can be more simple? Real line and absolute value. Example. Extract properties of this example. Extracting properties. This we did. And the crucial step, take these properties as axioms in abstract situation. Take them as axioms. So we have example. We can prove something inside this example, some propositions, theorems, and so on. Then select some of them, and call them axioms. And then tell what are the new examples which satisfy these axioms. So we did this. So this is definition of metric space. So now we forget about real life. These are now axioms. Definition. Let X be any set. Any, it can be space of functions, anything. Let X be any set. And let rho functional Cartesian product X by X to real numbers satisfy for axiom. Satisfy 1, 4. Then X row is called a metric space. Is called a metric space. Metric space. So any set where we introduce some function rho on Cartesian product, which satisfy these 4 properties, is called a metric space. And now we can construct examples of new spaces which satisfy these axioms. Of course, real line, this absolute value is the simplest example, but it can be many other examples. But before to go to new examples, I can tell that even with these axioms, we can play the game which mathematicians, therefore mathematics is tree which can go to up very high. We can take, for example, all axioms besides symmetry, beside this. So you get non-symmetric distance, where the distance from A to B is not the same as distance from B to A. For example, people in social science use such distances. So the distance from me to you is not the same as distance from you to me. At least in hierarchical society, if society is democratic, the distance is symmetric, and they used it. So you can forget about this. Triangle you should not take away, because what is another mathematical know-how? If you want to prove anything, you should have inequality. Without inequality, you cannot prove anything. So in metric spaces, this is the basic rule to prove something. If you develop new theory, you will get something non-trivial if you derive new inequality. So this is more or less know-how, how mathematics develop. So metric spaces, I shall give you additional examples, new examples. Of course, we can take Cartesian product of real lines, An. So it would be vectors with n coordinates. And what is another message? On the same X, we can introduce many rows. For the same points, we can introduce many different distances. So for one problem, one distance, for another problem is different distance, and so on. Even in numerical simulation, when you solve some problem, concrete engineering problem, it's numerical simulation work for one distance, but maybe it's not for another. For example, distance rho 1 between two vectors is just the sum g from 1 to n xg minus yg. And you can check that this distance, that should satisfy all these axioms, including this, because absolute value satisfy these axioms. We can introduce another distance. rho infinity x, y. It is maximum xg minus yg. So it is also distance. And we can introduce Euclidean distance, which is the most interesting for us, which is based on n-dimensional generalization of Pythagorean theorem. Rho 2 between 2 points is square root of the sum of squares of distances. When we are on the plane, it's just that hypotenuse is equal to the sum of squares of cathets. It is called Euclidean distance. Of course, Euclid never introduced it, but it's more or less his geometry of, so if this is A, this is B, this is C, so C is equal to square root A square plus B square. So it is multi-dimensional generalization of Pythagoras theorem. And if you studied linear algebra, we can even consider vectors. And vector C, it is the sum of vector A plus vector B. Okay, so these are distances. But we are not interested in such distances, because Fourier analysis is analysis of functions. So we would be interested in distance or metric on the space of functions. On the space of functions. And the simplest, we shall not use it, it's not our example. Our example would be more complicated. But this is example which illustrates where we want to work. Consider Sx by itself the space of functions. So the space of continuous functions from segment AB to real line. So points are functions. Points are functions. Each point of the space is function. And now we introduce the distance, which is in some way generalization of this distance when this G becomes continuous variable. Rho infinity between two functions, phi and psi. It is also maximum. Now with respect to t, phi t minus psi t. So this is the distance on functional space. Therefore, the corresponding science which work with such spaces and distances is called functional analysis. It's called functional analysis. It was introduced by a Polish Jewish mathematician Stefan Banach, who first started to do everything in this abstract situation with this abstract formulation of the notion of distance. Before, all people work, everybody with his own distance. They did not see that it is general framework. So somebody wrote PhD about this space and this distance, somebody about another space, and all results were you should prove for each distance its own theorems. And Banach was so clever that he thought, look, let us make this abstract framework and try to put something general for this rho. And then everything, for example, will come from general abstract theorems. Of course, some special distance have some special properties. It's also okay, but it's not enough for us metric space. Not enough for us metric space. We should, or if you want to come to Fourier analysis, we want to consider very special metric spaces which have additional linear structure. In all these examples, we see that these are also linear spaces in the sense of your linear algebra. In linear algebra, you have notion of linear space. So these are vectors. So this is distance on linear space. Here we can also introduce the sum of two functions. The sum of functions is point t, just sum of their values in point t. So all these spaces which we considered are linear spaces. And distances on linear spaces, they typically have very special properties. So more or less now it would be a recollection of your linear algebra with these elements of functional analysis. Okay, now we go to the case when metric space is linear space. Yeah, when metric space is linear space. We go to this situation. And so let now X be a linear space. A linear space. What is linear space? It's some set where its elements are called vectors and they're defined addition, subtraction, and multiplication by numbers, by scalars. So I will not put your all axioms of linear space, but for any number, which is, for example, real, and any two vectors xy from X, we can write linear combination or alpha beta, alpha X plus beta Y, and it is a new vector. It is a new vector. Multiplication by scalar is have all usual properties, for example, distributivity. Yeah? So one of important properties is distributivity. So if you get in course of linear algebra, you should have all axioms of linear space. So we can open brackets. We can open brackets and do everything what we want. What we want. So linear space, what we recall from linear algebra, the notion of linear space. Now we know complex numbers, and I don't know whether in your linear algebra your linear spaces were only over real numbers. Did you have the course of linear algebra? The first question you have, and linear spaces where scalars were real numbers, or you also consider it complex?
I think only real.
Only real, only real. But now we know complex numbers. We can generalize. For Fourier analysis, we need complex linear space. The notion of a linear space for scalars belonging complex numbers. So now any vector we can multiply by complex number, and we can make similar superpositions, similar linear combinations with alpha, beta, complex numbers. So we can write again alpha x plus beta y. This is z belonging to our space X. Formally, in abstract form, there is no difference. Moreover, if you had the course in algebra, you know the notion of field of numbers. It could be not only, maybe I tell you in 2 words, what is field? This is algebraic structure where we can very well define it: addition, subtraction, multiplication, and division to all besides 0. So real numbers is field. Complex numbers is also field. Here we also can multiply, divide, and everything. But there exist other fields. So not all fields here, only real or complex numbers. For example, there exists so-called residual class field, model P. And this you will study, for example, in cryptography or in my course elementary number theory. So in any event, now we have real linear spaces and complex linear spaces. No, maybe example of complex linear space. Examples of complex linear space. No, for example, X just C is one-dimensional complex linear space. One-dimensional complex linear space. So this multiplication is just multiplication of two complex numbers. More or less similar to real line. But of course it's plane. But when we consider it as complex linear space, we forget about that it is real plane. So now multiplication is scalars are now also from C. Scalars now are also from C. And in the same way as was for you, we can generalize and take Cn, Cartesian product of n times C. So that would be vectors with coordinates Z1, Zn, where each coordinate is a complex number. Each coordinate is a complex number. So complex linear spaces is no diff. All linear algebra for complex Hilbert spaces is the same as linear algebra for real, and in some think even better. In something even better, because for any symmetric operator we can solve why more or less some general remark, maybe not related to the course, why complex numbers are better than real. So more or less some superiority statement. Why is C better than R? For example, in signal analysis, everywhere you will see, in electrical engineering, everywhere you will see have complex numbers. So before you have already so big courses in real analysis, but in principle, in real applications, you typically work over complex numbers. Why? If it's starting the story from this equation, x squared is plus 1 equal to 0. In real numbers, we cannot solve it. In complex numbers, we can solve it. Yeah, so x equal plus minus I. And we can prove this theorem, it's called the main theorem of algebra, that any polynomial equation, a n z n plus a1z plus a0 equal to 0 has n roots in the field of complex numbers. So this is in some way amazing result, because how we constructed this? We added only one root, I, root of quadratic equation. Logically, it can happen that, for example, equations of order 3 would not have solution, or equation up to order 100 have solution, but order 101 do not. Complex numbers in something mystically are such that we solved only this equation, and then we can solve any such equation. If you find the roots, Z1, Zn, then as usual, we can expand this polynomial in the product of one-dimensional factors. So this is our polynomial Pz is equal to some number A, and there Z minus Z1, Z minus Zn. So this is the main theorem of algebra, that any polynomial with complex coefficients, Ag are complex, in particular real, can be expanded in the product of one-dimensional factors. So, and these people do everywhere in applications. In real numbers, we cannot do this. For example, when we are looking for eigenvalues of some matrix, we write characteristic equation. And it's can, in real, it's maybe have solution, maybe not. In complex, it always has solution. So therefore, all this, for example, in signal analysis, people should find the, they not always you can find eigenvalues. Sometimes they find so-called singular eigenvalues, but they all in complex, yeah. So it was a remark why complex are better. Now I suggest a break. We are already maybe half step of course of functional analysis, and we shall complete it soon and go to Fourier analysis. Yeah.
Jag tror som jag ser.
Ja, de hade testat så så det blev ingen reaktion.
Ja.
Sen är det de som sa det. Så då blir det skriver det på ritat papper också. Jag menar, det var
Nej, nej, det är bara för renskriva så det ska vara lite fint i alla fall. Du vet, jag måste skriva ner så för att kunna komma på någonting.
det var ju alltid en dator att skriva på annars.
Jo, men den var ner med läget.
Jaha,
Jag var
ja,
sen
okej.
Ja, jag visste aldrig setupen. Men det var precis blommor, såklart. Och så var det en sån här...
Sen låg du ett högt skick i sängen. Liksom i den pausen.
Det gick inte. Det var faktiskt sen. Sen var det en björn där vid. En liten allbjörn. Jag tror det var en ballong. Ja. Och så var det viltflaggen nästan.
Ja.
Jag kan säga sen om jag skrev. Inte allting. Men
Nej.
jag tycker inte chansen att dela med mig. Var det bästa delen. Dela med mig.
Eller så skiter du i hela världen.
Nej.
Bara. Jag vet inte att jag missar frågestunden om det blir rätt. Eller på veckan 5.
Du menar kantgrejen?
Ja, vecka 8. Jag blir erbjuden att åka till fjällen. Vecka 7. Onsdag till söndag. Så jag hinner gå på matteföreläsningar. Sen åker vi på eftermiddag. Sen kommer jag inte hem för typ söndag och måndag.
Okej.
Så jag tänker jag ska fråga Conny om vi kan få uppgifterna så jag kan göra dem på tisdag. Tisdag vecka 7.
Ja. Sa ni förresten det där med att man måste ladda ner...
Det glömde jag göra. Ja. Det måste vi göra på måndag. Jag påminner honom om det. Titta. Jag gör så här nu. Jag går in i min kalender.
Det här var det bästa delen tycker jag.
Ja. Jag ska säga om kvart över 10. Måndag 5 februari. Nu kommer jag inte glömma det. Bra. Eller jag kommer glömma det. Jag kommer påminna när det börjar.
Eller efter igen.
Ja.
Eller så kommer vi komma på det efteråt igen.
Det är typ, jag tycker att det är typ veckans höjdpunkt. Måndag.
Ja, kan vi.
Frågestunden i Conny. Jag tycker det är jättemysigt.
Jag gillar också den. Det är synd att dra hem.
Det var mycket att göra på måndag.
Det var fett. Och det var liksom, jag var desperat.
Ja. Jag var det påminner mig, det måste jag fixa.
Ja, och nu är min lägenhet funktionerar skit. Så det är för fan och stökigt där.
Jag skulle med vit choklad överallt.
Nej, tyvärr.
Men då hade det inte typ där.
Men nej, det är typ smyg och det är fan diskat.
Jag tror inte jag kan.
Jag skulle göra en... Ja just det, jag pluggade ihop på kommingen. Jag gick igenom föreläsningen och läste. Det är inte så mycket på många för världen. Jag var seg. Fan. Därför så kom jag istället på matten.
Ja. Jag och Max ska ta dem i eftermiddag.
Mm.
Men jag har glömt skriva till honom. Eller jo, nej, det har jag inte alls gjort. Det var inget.
Mm.
Det slutar bara att man sitter och skämtar med honom.
Jo.
Fast nu skämtade vi inte om dig.
Jaha.
Som vi gör i gruppchatten.
Ja, men det, då, man ska ju så mot varandra.
Ja.
Det måste vi.
Vad kul. Idag är det ju fotboll med. Jag får spela där på Tottenham.
Om Tottenham har just det. Jag försöker komma på vilka. Ni möter också City nästa gång.
Ja.
Under helgen tror jag.
Jo.
Fan, jobbig vecka.
Ja. Men vårt...
Fast City är inga fel.
Nej, alltså, jag fattar inte hur vi har så jävla bra record mot City.
Det gick det sist förresten.
Sist.
Alltså den här säsongen.
Vi har inte mött den. Den blev uppskjuten.
Okay. Ja, där.
Så vi har inte mött sen förra säsongen.
Ja. Nej. Du vet, jag hatar när City vinner. Men Liverpool får inte vinna. Speciellt lite när Klopp lämnar.
Det jag skulle precis säga. Det ska bli intressant att se när hur det blir när han lämnar.
Ja, då kommer det bli dåliga igen. Nu säkert har de blivit bättre igen, men det kommer bli dåligt.
Har du någon aning om vem som ska ta över?
Nej. Men jag chansar på att det blir Alonso.
Ja.
Du vet, han är i Liverpool.
Mm.
För att så vill inte Benitez gå tillbaka. Fast han är typ med i fall de inte hittar någon alls. Jag tror att han skulle kunna gå tillbaka till Liverpool. Han som floppade i Real. Och var sen lyckas. Jag tror Barca. För Xavi.
Jag vet att jag ska lämna. Men inte mer och så.
Jag gillar den här bilden.
Har vi ett plats?
Och då är det.
Där har vi ett huvudspel på dagens plats.
Ja.
Jag får frågan. Det är sen vilken grupp vi tillhör. Om vi tillhör de som ska ha teoridel eller inte.
Ja, vi kommer inte.
Det är så det är.
Så du får fan få
Bita ihop.
Ja.
Och lära mig.
Jag sa till dig från början, vad gör du?
Med den här kursen behöver vi faktiskt. Men det är inte bra fråga.
Ja. Ja,
Vi behövde inte det flera gånger.
ja, men då behöver inte som automat. Förstår du?
Nej, men det fanns fortfarande en kurs som gick där som hade teoridel också. Så jag menar.
Ja, vad heter frågan? Kom undan.
Dock, i analys 2 hade ju alla det.
Mm.
Och nu ska ju tydligen inte alla ha det. Vi tar det sen till Paulus.
So we continue. We continue. And you write another title, so we more or less, okay, maybe before remarks that not all metric spaces are linear. So, not all metric spaces are linear. So the metric space is the most general notion. And now we shall step by step go to more and more concrete notion. So the simplest example is the following. Take arbitrary x. So take any set x and introduce on this set following metric. The distance between 2 points is equal 1 when they are not equal and 0 when they are equal. So in some way, discrete distance. If we are different, the distance between us 1. If we are the same, the distance is 0. So you can check that it's metric, but X is any set. There is no any, it need not be vector spaces. So any. So on any set, we can introduce such trivial distance. But we are not interested in such spaces. Our aim is go to metric spaces, which are also linear spaces. So maybe before to go to such linear metric spaces, we make one more remark. Okay, we go to, let us write the title, normed linear spaces. The new word is here norm. The norm is direct analog of absolute value. So go back to real line. And here, of course, we have distance between 2 points. Have this distance. But we have something conditional. We have simply absolute value of x. So we have function x to its absolute value. And distance is defined with the 8 of this absolute value. So define distance between 2 points is take absolute value of the difference. Of course, here is important that we can subtract. So that it is linear structure. Now, in the same way as we did here, let us list the properties of absolute value. So what are the properties of absolute value? They are very similar to the properties of metric. Besides one property. So first, of course, this is non-negative. Second, 0 if and only if x is 0. Third, the third property is different. On the real line, we can multiply. Now we consider x as one-dimensional vector and multiply by some alpha, which is also real. First of all, we are, for the moment, we are on real line. Yeah. Then we get absolute value alpha x. And the fourth property is analog of triangle inequality. The same can be checked for x, which is complex numbers. And z is equal z star or x squared. It's not good here to use x and y because they were used in real case. So it has the same properties 1, 4, 1, 4. So it is again natural mathematical step. We have two examples with this function and this function, real and complex, which satisfy such properties. In the complex case, this is absolute value. Now let us declare that these are axioms. So these are axioms, and we will get a new notion. So absolute value on real, absolute value on complex, we unify under abstract notion of norm. So norm is an abstract generalization of x absolute value x and z absolute value z. So the formal definition is the following. The formal definition is the following. Definition. Let now x be a linear space over real or complex numbers. Be a linear space. And let x, the more or less, we cannot write just as usual absolute value because we would mix with this. We write to this guy, and let be a real valued function on x. I remind you that having a complex absolute value is also a real valued function. Yeah? So this is a real number. This is a real number. So now we make these axioms just we put everywhere. But he's not everywhere because now alpha is number, real or complex, and x is vector. Only here and here. So this is abstract list of properties of absolute value, which are now considered as axioms. Now they are considered as axioms. Then this map X is called a norm. And X with this norm is called a normed linear space. A normed linear, it is important, linear space. This is, now I told that linear, okay, we'll give examples of normed linear spaces. We shall give examples of normed linear spaces. Yeah.
Linear space is a synonym for vector space, right?
Oh, okay. In your course, you called it vector space, yes? Yeah. Vector space and linear space are synonymous. Vector space is the same as linear space. Some people use this terminology. More or less, the course is called linear algebra. It's in some case course on linear spaces, but vector spaces is also a very standard definition. Yeah. Example. In fact, all spaces which we considered were normed linear spaces, besides of this discrete distance, yeah? So, x equal Rn. And for example, norm x1, it was just the sum of absolute values of coordinates. Norm x infinity, it was maximum xg. And norm Euclidean, it was square root of the sum of squares. Square. So all spaces which we considered before were in fact normal linear spaces. And even the space of continuous functions, x equal the space of continuous functions, also has the norm. These are linear spaces, and these guys are norms. Now, normed space is a special case of metric space. Our new message. Any normed space is a metric space, and norm is introduced as it was before. So any normed space is a metric space. And how to introduce the distance? As it was absolute value of difference, it would be norm of difference of two vectors. So, and you can see that all metrics which I wrote before, they can be written in this way through these norms. And now I'm about to approach, of course, we should then maybe go back to clarify some notions, but I want to present the main line, how abstract Fourier analysis is formulated. Now we know metric spaces, and now we introduce even more special class of normed spaces. So we do more and more special constructions, starting with very general metric space construction. So these are normed spaces. Yeah, good. And now I go to the notion of Euclidean space. Maybe you even considered this in the course of linear algebra. Did you consider such notion as scalar product or inner product of two vectors? Yes, I think yes, because without them it's impossible to do. Now we won't consider not any linear space, but linear space with scalar product. No, I shall destroy this for the moment. Linear space is scalar product. How people let us write such a linear, we can write even in this way. Euclidean. Is it right or is I don't know. Euclidean spaces, which is the same normed spaces with linear with scalar product. So we need scalar product. We need scalar product of two vectors. How define scalar product in abstract way? Again, the machinery is the same. Consider some simple example. For example, finite dimensional space of your course of linear algebra. List the properties of scalar product and then take them as axioms. So we start. So for example, our x is Rn. Vectors have coordinates x1, xn, y1, yn. And the scalar product on this space is defined in this way. So this was the scalar product which you can use on Cartesian products of real lines. What are properties of this scalar product? What are its properties? More or less as mini propositions or mini theorems, which will be in future axioms. So first of all, if you multiply x by x, it would be the sum of squares of coordinates. So it is non-negative. Scalar product of x by x is non-negative. Because it would be sum with respect to g, xg squared. Second, scalar product is equal 0. So the sum of squares of coordinates is equal 0 if and only if x is equal 0. So these are more or less similar properties which we had for distance, for norm. Yeah. 3. It is linear with respect to both arguments. Or first, let us write that it is symmetric. xy is equal yx. So if we change coordinates by places, the answer is the same. So scalar product is symmetric. Scalar product is symmetric. Or it is linear with respect to both arguments. What does it mean, for example, for the first argument? If you multiply it by scalar plus alpha 1 x1, alpha 2 x2 y, then we can open brackets and make it as usual. So constants go out. So it is equal alpha 1 x1 y plus alpha 2 x2 y for any alpha 1 alpha 2 belonging to real numbers. So we can open brackets. If you put here in this formula, it's of course because it would be just linear combination of coordinates. Then, so for example, if you put it here, it would be g1 to m, alpha 1 xg 1 plus alpha 2 xg2 multiplied by yg. And then we just open brackets for usual real numbers. Since scalar product is symmetric, in fact, it's enough linearity only with respect to the first argument. If I now put this block to the second place, I can change the places and again open brackets. So these are abstract properties of scalar product. I don't know whether in your course of linear algebra your teacher formulated them or it was just coordinate representation of scalar product.
He did the same thing.
The same thing, yeah. So good.
Used
You see this not the first time, да?
Yeah, but I used this brackets instead
Mhm.
to know.
In some books, people use brackets, yeah. Yeah. We reserve this for complex case because we shall consider even complex scalar product, and it's a bit different from real. So practically the same with one or two differences. Okay, so this was this example. These were the properties of scalar product, which was defined in this way. And now we would like to make abstract definition. So the linear space with scalar product, which is called Euclidean space. Linear space with scalar product. Space with scalar product. So all these axioms would be preserved for it. Complex case we shall consider later, but we need complex for the analysis in complex space. So definition. Let X be a linear space, real space over R. Unfortunately, complex case have some difference. We should consider it separately. Linear space over R, and it have and let it have a scalar product. That a map from Cartesian product to real line, satisfying these four axioms, such that we have these four properties. Then let's call it Euclidean space. Then X with this scalar product is called a Euclidean space. Euclidean space. We can practically all properties of your course in linear algebra generalize to these Euclidean spaces, Generally, in your course of linear algebra, I guess that you had finite dimensional spaces, but these spaces generally are infinite dimensional. And now we consider an example of space which is interesting for us. Yeah. Consider example of infinite dimensional Euclidean space. But first we will introduce such notions. Or first give example. We first give example, on this example we shall illustrate. So for example, X is denoted L2 small. So this is the space of all sequences, infinite sequences. So these are vectors with infinitely many coordinates. So vector which has infinitely many coordinates. And which has such a property. There is a norm, and this norm is a Euclidean norm, more or less Euclidean norm, xg squared less than infinity. So this is this space. Who is in this space? For example, if you take sequence with coordinates 1, 1/2, 1/3, 1/n, and so on, it is in this space. Because if we consider the sum of squares, the series converges. If I take some sequence which decrease not so quickly, for example, I put here square roots in denominator. This series would be harmonic series, it does not converge, so it is not an L2. So these are all vectors with infinitely many coordinates. On this space, we can introduce scalar product. As it was in your course of linear algebra, but now sum is infinite. You can check the successful properties of scalar product. Of course, there is natural question why this series converge. Because our condition was that this series converge of squares. But now they are products. So of course it's important why does it converge. It converge. And there is some relation between scalar product and Euclidean norm. Okay, so let us prove this. Let us prove this because we would use this. Or maybe not prove. I want to go quicker. I prove next lecture this because it's technicality. So now I formulate such theorem. It's not derive as like engineers, but now I formulate theorem and then I will next lecture give its proof. Theorem. It's called Cauchy-Schwarz inequality. Again, all theory of Euclidean spaces is based on this Cauchy-Schwarz inequality. So everything is coming from it. How this theorem to write? Let X, the scalar product, be a Euclidean space. And let define per definition. Later we shall see that it's really a norm. We can make remark here. Later we shall see that this function x is really a norm, but for the moment we don't know this. It's just this function, square root of scalar product. We can write this function because scalar product is non-negative. So let's redefine it. Then the following inequality take place. Scalar product x, y is less or equal norm product norm. Where norm is defined in this way, square root of xx and square root of yy. This is precisely this famous Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. No, the proof is very simple, but it will take time and we shall do this later because I want not slow the line of approaching what we want to approach. In particular, if you now go to this question and to this space, in this space we will have this thing in this how it's ways. Well, it's good place to destroy this. So if we write this in L2 space, so it will have this thing that sum g from 1 to infinity xg yg is less or equal square root so less than infinity because of this. Because in this space for each sequence, the sum of squares of coordinates is less than infinity. I don't know, in your course of linear algebra, did you have this for n finite? such inequality. No analog of Cauchy-Schwarz inequality for finite dimensional case. It would be inequality sum from G to N, product of coordinates, and there is sum of squares again from 1 to N. You don't recollect that?
On the same course on
Hmm?
the we had Cauchy-Schwarz inequality.
You had this, huh?
Yeah, I had it.
You had this. Okay, so in any event, now we get, okay, of course, maybe it's not so bad to write consequence for finite dimensional case, yeah? How it's looked. In finite dimensional case, if you are on Rn, if you are Rn, no, we have the same, but here is until the end. So this is finite dimensional Cauchy-Schwarz inequality. This is finite dimensional Cauchy-Schwarz inequality. So scalar product can be estimated by norm. For the moment, we don't know that this is norm. We're just about to prove that this square root of scalar product is really a norm. So then what would be this is our final space where we want to work. It is linear space with scalar product where the norm and hence distance is defined in this special way. So our space where we want to develop Fourier analysis is linear space with scalar product, which automatically determine the norm and hence metric. So metric is determined by scalar product, and the norm is also determined by scalar product. Okay, let us prove theorem that this function, where it is really the norm. It is really the norm. No, look to this function. It's clear that it is non-negative. X equal to 0 if and only if the norm is equal to 0. If you multiply by lambda, maybe what has happened if we write lambda x, where lambda is real number, it would be square root lambda x. Then we can take away number and this number, so it would be lambda square. So it would be lambda square root, so it would be this. So it is also work. Scalar goes from this norm with absolute value. The most difficult is, as always, triangle inequality. Inequality is the most important and the most difficult. So we should prove that the norm defined in this way satisfies the triangle inequality. That the norm defined in this way satisfies the triangle inequality. Let us try to do this. So we want to prove that any Euclidean space is also normed space where norm is defined by scalar products. Theorem. Map X is a norm. So let us consider we want to get this. What we prove. We want to prove this inequality. Question. Since square root is not good guy, it's better to work with squares. So square is less or equal. So we want to place h square of this norm, which is defined as scalar product, is majorated by this. Now, how we do this? We have this Cauchy-Schwarz inequality. In Russia, it's called Kashi-Bunikovsky-Schwarz inequality because it was Russian who was more or less at the same time. Bunikovsky. But maybe nowhere outside of Russia people use this name. And of course, for Russians, it's the idea that they were the first everywhere, and everywhere there is Russian who discovered this before all people in Europe. So this is more or less historical tradition. So if you make some technical device, they always tell, okay, it was on the Ural Mountains, some engineer, and he used this, but only he won, and there's only one this device, yes, but it's in museum, yes. All children coming to museum look, oh, yeah, it was done by us, yeah. But nobody asked why nobody used this. So maybe in Russia were many such discoveries where some genius guy discovered something, but nobody else used this. It was no management. So the main problem was in Europe, there was great management. People discover and expand. In Russia was great problems. There were many clever people, but it's die with this guy. He discovered this device, used it, and he died, and device was destroyed. Yeah. Okay, so it is Bunikovsky. Bunikovsky also discovered this inequality, but nobody beside Russians know this. Okay, so this is just historical remark. Go here. What is this? Yeah. Now try to open brackets. Try to open brackets. Now, we see that this is the square of the norm. This is the square of the norm. This is symmetric, so we can write to this, and then use Cauchy-Schwarz inequality. So this is less or equal norm x square plus, I automatically use it. So it is less or equal to x y norm y square. Yeah. But this is precisely this guy. So this is precisely what we wanted. X plus y square. So this norm defined with the help of scalar product satisfy triangle inequality. So it is really norm. So it is really norm. So we have that any Euclidean space is also normed space, and hence it is metric space. It is metric space. It is metric space. Now I'm ready to introduce this special Euclidean space where Fourier analysis is developed. So where abstract Fourier analysis is developed. I can say Euclidean space for Fourier analysis. In fact, Euclidean would be not enough. We should have one more notion, but maybe next lecture. So, consider X L2 of segment AB. So this is the space of functions from AB to real line. So it is functional space such that norm phi 2 square, it is integral AB phi or phi square, we can write phi square t dt is less than infinity. Square integrable functions, the space of all square integrable functions, the space of all square integrable functions. So this is the main space which is used in wireless communication, in electrical engineering, in signal analysis. What is the meaning of this square of this norm? what is the meaning of this square of this norm, of this integral? It is the energy of signal. So this integral AB pi square t dt has the physical meaning of energy of the signal t to phi t. Of course, signals are typically complex, so we should later consider complex valued functions, but yeah. This space, why it's natural? Because all signals have finite energy. No, we don't have signals with infinite energy. So this is the most natural space for any engineer, for any physicist. All signals are in this space. Of course, maybe there are too many signals, but at least all are in this space. All are in this space. There's one mathematical difficulty, not so trivial, but physicists, engineers, technicians never pay attention to it. This is this integral. This is this integral. Because maybe you studied only Riemann integral. Riemann integral is not enough. You should use so-called Lebesgue integral. And this is integral. This is special course integration theory. But Lebesgue integral, no, it's much more difficult theoretically, but properties are the same as Riemann integral. So you can work with this dt as you worked with Riemann integral. Don't afraid, you will never get wrong result. But on the real mathematical level, it is not so simple. I suggest at this moment finish because we have too many notions, and if you would be able to put them in brain during 1 week, it would be already good. Yeah. Next week, this space would be used to write Fourier series. Fourier series would be maybe last remark. Take an orthonormal basis, as in your course of linear algebra, and expand this function with respect to orthonormal basis. It would be abstract form of Fourier series. Then to get, for example, this is basis. You need not write this, it's just what we shall do later. Now, if you take this En sinus and T and En prime cosinus and T, so there are two types of vectors. Then expansion of our function with respect to this basis would be Fourier series. So we come, typically people start with these two functions, cosinus and sinus, and try to write function as a linear combination. We go very abstract, and then this will be just example. What is my main aim? That typically convergence, we should study next lecture, convergence of this series. In signal analysis, it is in this space. It is in the norm. Because mathematicians, they want convergence of the series in each point, In real applications, it's not always. Signals can be very, so, and they're very good for integration. But maybe they are not good for uniform convergence and for convergence which people use in mathematics. But we also consider mathematical theorems when the series converge in good way and so on. Okay, so it's enough for today and we finish. Yeah. So we put maybe half course of functional analysis. Yeah, so this is maybe you will have in future, but it will be more detailed.